Here's another video of the lecture intropde. In this video we present section 5.5, and in this section we present the solution of the wave equation in odd dimensions. Before we, in general odd dimensions, we already have done this in dimension 1 and in dimension 3, and now we will see how to generalize to general odd dimensions. Yeah? In particular, we will again use the Euler-Poisson-Darboux equation and transform it as in dimension 3 into the one-dimensional wave equation. For this we need some preparation, namely we need this lemma. Yeah, and this lemma has three statements. Yeah, we have such an operator taking derivatives. Here this is second derivatives, and this is d by dr square, and then 1 over r times d by dr to the power of k minus 1, and then r to the 2k minus 1 phi of r. Yeah, this is the same as 1 over r d by dr, and now to the power of k, and r to the power 2k, and then we have d phi by dr of r. Okay, here this is the first statement. Yeah, and the second statement is that the expression here, only this expression here, in part E, we show that this is a sum over j equals 1 to k minus 1. And then we have some coefficients, some real coefficients, beta k, kj, and then we have r to the power of j plus 1. And we have the j derivative of phi of r with respect to r. Okay, and in the third, this is here the second statement, and this third statement is here we only calculate one of these coefficients, namely we calculate the coefficient beta k 0. So if j is 0, the lowest term, and then the claim is 2k minus 1 faculty divided by 2 to the power of k minus 1 and k minus 1 faculty. Okay, let's prove this. Yeah, proof of I by induction. Okay, so we start for k equal 1, k equals 1, as induction means we first consider k equals 1. If k is equal to 1, then we don't have this term. So then we have d by dr square of r to the power 2 minus 1. This is 1. So r times phi of r. Okay, let's do the calculation. What we get, we have the Leibniz rule d by dr, and then we have phi of r plus r times phi prime of r, and this is, of course, now we do the second derivative, and then we get phi prime of r, and phi prime of r, plus here we get another phi prime of r, plus, and then we get r times phi double prime of r. Okay, and the right hand side, what is the right hand side? This is 1 divided by r, 1 over r d by dr times r times d phi of r. No, 1, sorry, 1. Yeah, we only have this. and now we have r times phi prime of r. So let's do the calculation. Yeah, this we already calculated, so it's sorry, it's r square here, r square. So if we do here the calculation by the Leibniz rule, we get 1 over r, and we have 2r phi prime of r, and the other term is we have r square of phi double prime of r. And now if we take this in, then we have 2 times phi prime of r plus r times phi double prime of r. Yeah, and this is of course the same as this. So this shows the case k equals to 1. Now now we do the induction. So let us now assume that the formula holds for k, some natural number k. Okay, and now we want to prove it for k plus 1. Okay, what we do, then we have d by dr, 1 over r, d by dr to the power of k. If k minus 1 plus 1 is k, r to the power of 2k plus 1, phi of r. Okay, what we get? Then here we have a square. Yeah, so now we apply once this operator. Once this operator that we now can apply this formula. Okay, so we apply once this operator, then we have this is d by dr square. And now if we take here the derivative and 1 over r d by dr to the power of k minus 1. And now what we have? We have 2k plus 1 times r to the power of 2k times phi of r by the Leibniz rule. And 1 over r we have here still missing from this. And plus r to 2k plus 1 phi prime of r by the Leibniz rule. Now let's put this r inside, and we have d by dr square 1 over r d by, no bracket, d by dr, this whole power to the k minus 1. Okay, and what we have is 2k plus 1 r to the power of 2k minus 1 phi of r plus r to the power 2k phi prime of r. Okay, and now we can apply this formula. Yeah, so now we want to apply this formula. Okay, in order to apply this formula, we need this factor in front. So this is, let's put this factor in front. 1 over r d by dr k minus 1 r to the power tk minus 2k. And then we have 2k plus 1 times phi of r plus, here we have 1 more r plus r times phi prime of r. Okay, and now we can apply this formula because we know that this formula holds, of course, for all functions. Yeah, let's call this phi tilde of r. Yeah, then we know by the formula this is 1 over r d by dr to the power of k r to the power of 2k. And now what we have d phi tilde by dr. Yeah, here we applied the assumption, the assumption that the formula holds. Yeah, we assume that the formula holds for k. Yeah, so if we call this phi tilde and apply this formula, then we obtain this. Okay, now let's calculate what is the derivative of phi tilde k. No, then we have 1 over r d by dr to the power of k, r to the power 2k. Okay, when we take the derivative, yeah, then we get then we have here the derivative of this function. This is clearly 2k plus 1 times phi prime, not phi tilde, phi prime of r, plus, and here we get another phi prime of r by the Leibniz rule, plus phi double prime of r. Okay, and now we want to see whether this is this expression here. Yeah, and okay, let's now calculate the right-hand side, what we have, what we should get out here for k plus 1. Yeah, so this is what we get by the left-hand side for k plus 1, and now let's calculate this. 1 over r d by dr, k plus 1 acting on r to 2k plus 2 d phi dr of r. Okay, now here we have one extra power, so this extra power we should calculate. So this is of course 1 over r d by dr power of k, as we have it here. And then we get an extra derivative. So we have times 1 over r, and now we can calculate the derivative. This is 2k plus 2 times r to the power of 2k. Yeah, 2k plus 1, taking the derivative, times d phi prime of r, derivative is also the same as phi prime of r. And then by the Leibniz rule, we also have to take this derivative act here, plus, so we should write, yeah, here we have the bracket, plus r to the power 2k plus 2 and phi double prime. Okay, now we yeah, this is what we should get. Okay, let's see. The first term d by dr, this is already the same. Now we multiply this, and then we see we get 2k plus 2 times r to the power 2k times phi prime of r plus here we missed this r. Here's an extra r. Okay, plus r times phi double, r to the power of 2k plus 1 phi double prime. Okay, and this is indeed the same as this. Yeah, since we have this 2, this add up exactly to this term, and r times this adds up to this thing. Yeah, so the formula for k plus 1 follows. yeah, by induction, the formula holds for all k in n, all natural numbers. Now let's see the second statement. Yeah, now we want to see that this expression here, that this expression has indeed this form, yeah, a polynomial. So every derivative here, this is of course a derivative, yeah, 1 over r d by dr to the power of k minus 1. This is of course the same as 1 over r d by dr times 1 over r d by dr, and so on. Yeah, and so this means k times k minus 1 times this factors, and the last factor 1 is d by dr. So every derivative, yeah, now this means this is a product, acting a product of such derivatives and powers of r. Every derivative acts by the Leibniz rule, yeah, on powers of r times phi of r times phi times, some derivative of phi. Okay, let's see, we have some a to the power of k and phi l, elf derivative. Yeah, as we get two summands. One is k r to the power k minus 1 phi l of r plus r to the power of k phi l plus 1. Yeah, so l plus 1 of. So this means it on the one side it diminishes the powers of r by 1 in one term, and in the other term it increases the order of total derivatives. Yeah, it orders it enlarges the order of the derivative. Now, how many derivatives we have, or how many powers of r we have? How many powers of r we have first in this expression? Yeah, we have all together. Yeah? We have 1 over r to the power k minus 1 times r to the 2k minus 1, and this is of course r to the power of 2k minus 1 minus k minus 1, and this is r to the power of k. Yeah, so we have a kth power. And how many derivatives we have? Yeah, so we have d by dr to the power of k minus 1. So we have k minus 1 derivatives. Now, if any derivative enlarges, either diminishes this power of r or enlarges this power, yeah. So all terms which we obtain if we do the calculation, also if moment, sorry, here. Oder not all term, the term which we obtain. Oder, no, sorry, all terms was okay. All terms which we obtain if j of the derivatives acts as derivatives on phi, and k minus 1 minus j diminishes the order of r. R are multiples of, then we have how many powers we have? We have r to the power of k minus, and now k minus 1 minus j times, and we have j derivatives. So phi j of r. Yeah, and what is this power here? K minus k is of course 0, minus minus is 1. This is r to the power of j plus 1 phi j times r. So it's really exactly of this form. Yeah, of this form here. Okay, and j of course can vary from 0 to k minus 1. Yeah, because here we have only k minus 1 derivatives. Yeah. Okay, this proves the second claim. Now we come to the third claim. For beta k0, this means all derivatives acts on the powers of r. Yeah, this acts on the powers of r. Okay, now let's see how they act. The first derivative, also the derivative which is to the right, yeah, to the very right of all, sorry, here, of all these powers, yeah, the derivative which is to the very right. Also, the derivative to the very right acts on, okay, clearly r to the power 2k minus 1. So this gives a factor, this gives 2k minus 1, r to the power 2k minus 2. Okay, but the power is not interesting, yeah? Okay, and now the second, what is the derivative? The next derivative. Yeah, this acts on which factor on which power of r it acts. Yeah, we have here one additional r, so it acts on r to the power 2k minus 3. So this gives, so it gives 2k minus 3 and r 2k minus 4. And now the next, and so on. And so on. Yeah, the last, the k minus 1, yeah, because finally, yeah, so we have all together k minus 1 such operators. So hence this shows, hence beta k0 is equal to, we have 2k minus 1, 2k minus 3, and so on. And the last factor then is, we have 2k minus 1, and now we have to subtract how much? Altogether we have k minus 1, but every time we add 2, so 2 times 2, not 2, but k, 2 times k minus 2. Because for the original we have this, there we subtract 0. So what is this? This is 2k minus 1 times 2k minus 3. And here we have 2k subtract, so it's the last term here is 3. Of course, we may also add another 1. This doesn't change. Okay, so this is the factor beta 0k. Now, how we can write this? We can write this also as 2k minus 1 faculty, but then of course we have we have the even factors we have to divide out. So we obtain 2k minus 2, 2k minus 4, and so on, and the last factor is 2. Okay, so now collect these factors again. So we have 2k minus 1 faculty. Now let's write this differently. This is 2 times k minus 1 times k minus 2, and the last factor is sorry, we have of course another k, and the last factor is, so here we have 2 times k minus 2, and finally we have 2 times 1. Okay, and now we can write this. This is 2k minus 1 faculty. How many factors we have? 1 and k minus 1. So 2 to the power k minus 1 times k minus 1 faculty. Okay, so this is the formula for beta. Okay, this proves the third statement. Okay, and therefore the lemma is proven. Now this proves now the lemma. Okay, and now we want to calculate, we want to go on. Now we consider dimension 2k plus 1. So now we solve the homogeneous wave equation in odd dimension, so in dimension 2k plus 1. K is natural number, so all dimensions including 3. And now we assume that first we derive a formula. So let's start that we have a solution. So let U be such a solution, and we assume that it's k plus 1 times differentiable. So it's a solution of the initial value problem Okay, wave equation. Minus Laplace u of x t is 0. Yeah. xt r 2k plus 1 r plus, and u of x0 should be g of x, and du by dx of x0 should be h of x, as usual. Now we define u tilde. Yeah, now we use our formulas. Yeah, so we apply this procedure. U of x, r, and t. This is now 1 over r d by dr to the power of k minus 1, r to the power of 2k minus 1 times the mean. And similar, the same thing we do for the initial values. Yeah, so we apply this operator, d by dr to the power k minus 1, r to the tk minus 1, g of x r, and the same h tilde of x r, 1 over r d by dr power k minus 1 r to the 2k minus 1 h of x r. And then now we have a lemma, and now the claim is that this new function u tilde now solves the initial value problem of the one-dimensional wave equation with this boundary condition. Yeah, with this boundary condition. Okay, so let's check this. Yeah, then this is the this is exactly this initial value problem which we solved at the end of the first section. Yeah, so we see again we arrive at the same initial value problem which we already used in dimension 3. Okay, proof of lemma 5.4. Okay, let's do the calculation. Now the main thing is to show this. Yeah, this here, this is more or less clear, and since we have here this higher power, yeah, okay, let's start with this point. Yeah, that this is this form. For this we use exactly the lemma here. Yeah, we know that if we apply this operator, then we see we have powers, but the lowest power is with r. We always have powers in r, but the lowest power is 1. So it vanishes because we already have proven before that the derivatives, they are continuous. Yeah, so by lemma 5.2, the derivatives of u of xrt d by dr j are continuous. Yes, and we have chosen the k exactly right, yeah, for j equals 0 until order k minus 1. Yeah, in this lemma we have one extra derivative here of the u, Yeah, we assumed that the u, since the u is the mean, yeah, the mean is since we assumed that they, that they are k plus 1 times differentiable, then of course they are all continuous. So then u tilde of x, this should be on t, of x0 t is equal to 0, yeah, for all xt in R 2k plus 1 cross R plus 0 by lemma, by this foregoing lemma 5.3 and the second statement. Okay, so this proves now. And now this proves this. Now let's derive this difference. And this is also then clear. Yeah, this is also clear just because because everything is linear. Yeah, the initial values are clear by linearity. Yeah, of this operator. Okay, now we have to do this calculation. And for this, we do this calculation. We take this derivative. And then we have exactly this expression. And again, now we use this lemma here. We use this lemma, so this means we have this expression times k, 2k, yeah, power of 2k. So we insert this here. Yeah, this is exactly this formula which we had here, this formula. So then we have this expression here. Okay, now we do one term we leave and the other one we calculate. Yeah, we do then again this calculation. And then we have here, we have to take one derivative. Yeah, also here we let act both derivatives on the u, and we have 1 over r, so we get this term. Yeah, and here we let act this derivative on this power, so we get, since 2k, so we get this 2k, and this diminishes by 1, and we have 1 over r here from the first factor. This diminishes by 2, so we get this 2. Now we have these two factors as these two terms, additive terms, and then we see, yeah, 2k is nothing else but n minus 1. Yeah, and here we subtract this term, and then we see we have here less, so this means this is n minus 1 divided by r times this term. Yeah, and this is exactly what we had in the Euler-Poisson-Darboux equation. Yeah, let's see, Euler-Poisson-Darboux equation. What we had, this is here, n minus 1 over r. Yeah, so second derivative and n minus 1 over r. So this is exactly now by the Euler-Poisson-Darboux equation, this is the same as second derivative with respect to t. So this whole thing is the same as this expression here. So this is the same as this expression here, second derivative with respect to t, and this is clearly the same as this expression. Yeah, here this we replaced by second derivative with respect to t by the Euler-Poisson-Darboux equation. Yeah, because this minus this term without the powers of r is 0. So therefore this is equal to this term. And then we obtain this. So we indeed see that we have this equation. Okay, this proves now this lemma. Very nice. Now we know the solution. Yeah, we solved this equation. This initial value problem we solved. So we get this equation. Yeah, this is now a direct consequence. We get this equation. Yeah, this is a direct consequence of our solution. Yeah, and we only insert for a smaller or equal to t. And then of course we are interested in this term here. Yeah, we are interested in the value itself and how we can calculate the value itself if we know all the means. Okay. Remember, in 3 dimensions we took the limit that r goes to 0. So this we will do again here. Yeah, u of x t is r going to 0 of u of x rt. But this, now remember that we have this as this formula here. Yeah, and here we have higher and higher powers. If we divide this by r, then there remains always a positive power, with the exception with the only for j equals 0, there remains no term. So this quotient has a nice limit, and in the limit it's exactly the limit of this, and this is this. Yeah, so we have this nice formula. Now we have a complete formula for our solution. We have to take this limit. So let's write this limit. U of xt is, remember here we insert 1 divided by beta k0. Yeah, beta k0. No, what was this? No, this was, in the lemma we calculated it. Let's write it again. So it's 2k minus 1 faculty 2 to the power k minus 1 times k minus 1 faculty. Okay, so now we insert this term here, and then the inverse of this factor, this is this term here in front, and so we have to take here this limit, yeah, of this. Okay, so here we have to take this limit. Here, yeah, this is exactly the 1 divided by 2r is the length. Yeah, so this means we get the mean. Instead of 1 divided of 2r writing in front, we take the mean. Yeah, the 1 divided by 2r we get, since we have this 1/2, and we divide by r. This factor we already have in front. So we on the one side we have this term, and on the other side we have this term. Yeah, and then here we do again the trick with the derivative. Yeah, maybe I write it explicitly. G tilde of x t plus r minus g tilde of x t minus r divided by 2r. Okay, this we may write g tilde of x t plus r minus g tilde of x t divided by 2. Yeah, and then 1/2 plus g tilde of xt minus g tilde of xt plus minus r now, minus r divided by, here this should be an r. This is again, okay, and this is clearly, this is derivative, so we get dg tilde of xt divided by t. Yeah, so this the limit r going to 0. Here is missing also the limit r going to 0. And then we have this. So we have now a complete formula. So we have this formula. Okay, so now we can state our main theorem where we have this solution, yeah, which claims how the solution looks like. Okay, we need some derivatives. Maybe first later we will see how many derivatives we need if we have the formula. Yeah. Now here let's write. We have 2k plus 1 is n. Yes. Then what is k minus 1? What is k? K is clearly then n minus 1/2. And k minus 1 is then what is k minus 1? This is n minus 1/2 minus 1, and this is n minus 3/2. Okay, so this is k minus 1. Yeah, what is what were the other terms which we had? Yeah, the other terms which we had here for the in this operator, this is 2k minus 1. Yeah, 2k minus 1. This is clearly n minus 2. Yeah, so this is n minus 2. Okay, so in this way we really get this powers here, 2t to the power n minus 2 and this operators. Yeah, and this is here k minus 1 we already calculated, so these are these factors, and this is again 2k minus 1. So this is now this factor, and this is the whole thing here. Yeah, and here we have an additional d by dt. We have an additional d by dt. So now this is our formula. So this is now an explicit formula, complete formula for the solution of the wave equation. Now let's prove this for you. Yeah, what we have to prove. Proof of theorem 5.5. Until now, this is true also in dimension 3 and in dimension 2. Until now, we haven't really proven that the formula which we obtained really solves the the homogeneous wave equation. We have not proven also in dimension 2 and 3 that our formulas really gives solutions of the homogeneous wave equation. So now we will do this in the general situation, also first in the odd case, and later we will show this in the even case. Yeah, and this is this long calculation here. Yeah, so we proved that this really solves the homogeneous wave equation. Yeah, and then we will see that it really solves the initial value problem. Yeah, and the initial value problem. Now we give a complete proof that this is really true. Okay, this is some nice calculation. Okay. This is of course linear. So we may consider the two cases independently, yeah, as we did also in the heat equation. We may either take G equals 0 or we may take H equals 0. We start with the case that G is equal. So we first consider the case that G is 0. Then we only have this term. So, and now we show independently that this term alone solves the homogeneous wave equation. So let's do the calculation. We calculate the second derivative. So we have this factor in front, then we take the second time derivative. Of course, the second time derivative commutes with this. Okay, so we have this formula. Now we apply this. We call that this is k minus 1. So we apply this lemma, the first point. Yeah, we apply here. We apply this statement here. Yeah, k minus 1, this factor, a second derivative. And then we get factor k, power to the 2r to the 2k, and so on. So now we apply this nice formula. So we get one higher term, k. Yeah, k is then n minus 1 over 2. Yeah, k n minus 1 over 2. 2k is also n minus 1. This is this term. And then the derivative of this function here. Yeah, derivative of this function. So now we have to calculate this derivative. Okay, we always do the derivative by choosing the domain such that it does not depend on t. So we write this in this form here. Yeah, and the mean the mean of this ball is n times omega n. Yeah, so we first do this transformation that we use instead of the coordinates y. So we have y is equal to x plus t z. Yeah, so z is the same as y minus x divided by t. Yeah, t is the radius of the ball. Okay, and then the map z going over to x plus t z, of course, maps b this ball, the boundary of the 0,1 ball, onto the boundary of the xt ball. Yeah, this is clear by this formula here. Yeah. Okay, so and then by this reparametrization, now we take the mean over this ball, but the mean over the 0,1 ball is just 1 over n times omega n. Okay, and then this derivative. Now, here, now we can calculate this derivative, d by dt. Yeah, this we have done several times, so we put it in the integral, take the differentiation, then we get inner derivative z, and outer derivative is the gradient times z. Yeah, this is just this derivative. Okay, and here we again have this factor, so this is very nice here. Yeah, this is exactly this derivative. And now now we put this in. Yeah, and remember, now we reverse this coordinate change. Yeah, but clearly dny is of course d sigma y by this coordinate transformation we get a power t to the power n minus 1, yeah? Yeah, by rescaling, we get this power t to the power n minus 1. So by the transformation, by replacing the coordinates z by the coordinates y, yeah, we have to get back this factors. This is of course vector of length 1, so it's the normal, the outer normal. So we obtain this, and then now we can apply the Gauss formula. Yeah, now we can divergence formula. Yeah, so this integral over the boundary is of course this integral. Now the divergence of the gradient is the Laplacian. Okay, so we get this. Yeah, so this is just here. This is the divergence theorem. So we get this. Now we let act one more of differentials. Yeah, we let act here. Yeah, because remember at the beginning we had two t derivatives, so we get rid of two t derivatives. Yeah, but now we can apply one derivative, and by the polar coordinates, remember that the integral over the full ball is nothing else but the integral over the boundaries of the ball and then integrate by the radius. And here by taking the differential with the radius, we just get back this term. Yeah, this we had done several times. Yeah, so here we use this polar coordinates, write this as an integral over s going from 0 to t, the s over the integrals of the ball here with radius s, and then by the fundamental theorem of calculus, the one t derivative we can calculate here, yeah, and so we get this term, yeah, and one additional factor 1 over t we have here. Look at this. Here we have this additional 1 over t. Since one derivative we calculated, and then we have this additional 1 over t. Okay, so this is also clear now. And what we do now, we translate it, and to rewrite it as a derivative with respect to x. Yeah, if we rewrite it in this form, then here it's derivative with respect to y. Yeah, but for the sum, dx h of x plus y is of course the same as dy h of x plus y. Yeah, the derivative with respect to y is the same as the derivative with respect to x. Okay, so we now have this term, yeah, and then and here this now we rewrite it as the mean, but the mean has the power 2 to the power of n minus 1, yeah, but here we have 1, so the missing powers are t to the power n minus 2. Yeah, so we have 1 over n omega nt. This is the same as t to the power n minus 2 divided by n omega n t to the power of n minus 1. Yeah, we just multiply on the top and on the bottom by t to the power n minus 2. Yeah, then we have here on the bottom we have t times t to the power n minus 1. This is, yeah, so we have this term. Okay, and this is exactly the volume, so this gives the mean. So we get rid of this factor by rewriting here this as the mean, and this is of course here this, because all these things doesn't depend on x, so this Laplacian we can put outside, so we have this. Yeah, so this is the Laplacian of the whole thing, which is exactly this. And now we have seen indeed this solves the the homogeneous wave equation. Now we have verified that they really solve the homogeneous wave equation, okay, in the general situation. Now it remains to show, now we do the other case, yeah. In the other case, when h is 0, yeah, let's have a look. If we look, if h is 0, what we have then? Okay, now we consider what is the difference between this term and this term? The only difference is we have an additional t derivative. But if we have a function, yeah, if we have a function which solves, also if u solves d squared by dt squared u of xt minus Laplacian u of xt is 0, then clearly du by dt also solves this equation. Yeah? dt squared d by dt u of xt minus Laplacian u du by dt of xt is also 0. Yeah, because everything commutes. So we can put this d by dt outside, and if this is 0 and apply d by dt, then it's also 0. Yeah, so this also solves this equation. Okay, so this shows that also the term with the, so this means this shows this solves also the equation. If we just take h to 0 and g non-zero, yeah, then because then we have this term, and this also solves the homogeneous wave equation. Now to finish the proof, we need only to show that the initial values are the correct ones. Yeah? So what we need to show, also to finish the proof, we need to show that limit t going to 0 from ux of t is equal to g of x, and limit t going to 0 from du by dt of at x and 0 is h of x. Okay, then let's have a look on these formulas. Yeah. Here are the formulas for our function. Okay, we already have seen that this integral here, this integral, also without this dt and with this 4 factor, yeah, this is exactly applied this operator of the lemma 5.3. So it's this operator acting on the spherical mean of g and of g, and in the second term of h. Okay, and now we again apply this formula here. Yeah, so and since we want to take the limit t going to 0, and the radius is t, yeah, so we only have to consider the lowest term. Yeah, so we only have to consider the lowest term, and this means for the, here, this is the calculation, and so this means for this formula, for the value, yeah, since we have to take the limit t going to 0, and then, yeah, the factor in front just cancels with the beta k0. So it remains this term and this term. Yeah? We just have to take into account the lowest terms, and so we get this and this term. Yeah? And this factor here, this factor is exactly 1 divided by beta k0, and so we consider the lowest term, which is beta k0. So we get this formula here. Now, if we take the limit t going to 0, yeah, of this derivative, by the Leibniz rule, we can apply this derivative to t. Then we just get this integral. Or we can apply it to this integral here, to this boundary, but we already know that this is continuous. Yeah, so then this gives the number times t, and then if we take the limit t going to 0, this term vanishes. So it remains only the term here from this where we apply the derivative to t, and then we get the mean of g on a small ball, but by continuity of g, this is exactly the value of g. So we really get g of x of this term. And of this term, since we have this t, and this goes to the value h of x, we get 0. T times, yeah, t goes to 0 in this limit. So here we don't have a contribution. Now, keep in mind that we already have seen, yeah, that this whole integral here, this expression with this factor, but with this derivative, this obeys the wave equation. So if we take the second derivative of this whole expression, then it's equal to taking the Laplacian. Yeah, and for this reason, if we now take the t derivative of this expression here, then we get here a second t derivative, and then this is the same as applying the Laplacian. So we get this formula here, yeah, in the limit. And here we just apply the differential to this term, and we get this term. And now it's the other way around. Here we get, in the limit from this integral, the value of the Laplacian of g at x times t. And if t goes to 0, this goes to 0. But here, if we apply the derivative to this term, then we get h of x. And if we apply the derivative of this term, then we get something times t. And if t goes to 0, then this whole thing gets to 0. So we only get h of x. And this shows that this indeed has the correct initial values. Now, this proves the theorem, and now we have again some conclusion. Yeah, and the conclusion is, since u of x and t only depends on the values of g and h on the ball b of xt. Then again we have this. So if we draw this here in the plane, we have here, let's say, some x, okay, and some values of x, and here we have t. Yeah, let's say x1, x2, and so on. Okay, and then we have some value t, let's say here t. Then, yeah, this, then we obtain here this ball b of xt, and we see that the lines from the boundary of this ball, the lines, all the lines which going from one point of the boundary to this point, the straight lines, they all have velocity of length 1. So the length of the speed by which the solutions propagate this is 1. Yeah. The length of the speed is 1. Yeah, it's completely equal to 1. Yeah, and we also see, yeah, that u is, since we here applied an operator, a differential operator of n minus 3/2 plus 1, so n minus 1/2. Yeah, we applied n minus 1/2 derivatives on the function g and n minus 3/2 derivatives on h. Yeah, and for this reason, the function itself is n minus 3/2 times less differentiable than h and n minus 1/2 times less differentiable than g. Okay, so for this reason, this is an important difference to the heat equation. Yeah, the regularity diminishes, is smaller than the regularity of the initial values, and the speed of propagation has absolute value 1. These are two important differences to the heat equation. Okay, what we have done today, we solved the homogeneous wave equation in odd dimensions with the help of by solving the Euler-Poisson-Darboux equations. Yeah, we transformed them by some tricky transformation into the one-dimensional wave equation with some special boundary condition, and then we solved the in this way we solved the homogeneous wave equation and obtained explicit formulas. Thank you.